Hi, my name is Abdullah Abdulaziz. I'm a postdoctoral research associate at Hurriyet University. In this presentation, I'm going to present a semi-supervised Gaussian mixture variational autoencoder for solving the pulse shape discrimination problem. This work is a joint collaboration between Hurriyet University and the University of Illinois. In this work, we address the task of classifying different types of pulses for radiation sources. This task is encountered in a variety of applications, including characterization of nuclear physics interactions and safeguards of nuclear materials. As for many other classification problems, the main challenge is that obtaining class labels for entire datasets is expensive or sometimes impossible. In particular, the shapes of neutron and gamma ray pulses are increasingly similar as the deposited energy decreases. Hence, their discrimination is challenging at low energies. Therefore, classification methods that utilize both unlabeled data jointly with trusted labeled data are needed. Semi-supervised classification methods rely on the properties of unlabeled data to improve the decision boundaries and increase the classification accuracy. The variational autoencoder, or VAE, generally consists of an inference model, a generative model, and a latent space. The essence of the VAE is to learn a low-dimensional latent space representation that can accurately capture the important features of the high-dimensional dataset. The Gaussian Mixture VAE, or GMVAE, is one of the variants of VAE, which can be used for joint nonlinear dimensionality reduction and clustering or semi-supervised learning. The advantage of the GMVAE is that it can learn discriminant features from both labeled and unlabeled pulses, hence improving the classification accuracy. The observed data X are assumed to follow a generative process of the following form. The discrete latent variable y representing the data class follows a categorical distribution with k classes. The continuous latent vector z follows a Gaussian mixture distribution with parameters μz and sigma z. The data given the latent vector follows a Bernoulli distribution with parameter μx. The parameters of the distributions are given by the GMVAE generative network with parameter theta. The objective of the GMVAE is to approximate the posterior distribution of z and y given x, which is intractable and typically approximated by a factorized posterior, namely the inference model. In this work, we approximate the categorical distribution using the Gumbel softmax concrete distribution. The parameters of the inference and generative networks, theta and phi, are learned by maximizing the evidence lower bound elbow, that is a lower bound on the log probability of the observations. Until now, the GMVAE is trained in an unsupervised fashion. To increase the classification accuracy, prior knowledge about labeled data can be incorporated into the model in the form of auxiliary loss functions. We start by assigning labels to unlabeled data based on the k nearest neighbors KNN rule. Given the fact that data points belonging to the same class typically share similar features in the latent space, each unlabeled pulse is classified by the majority label of its KNN in the latent space. Motivated by the fact that KNN classification is dependent on the way that distances are computed between different pulses, KNN classification can be greatly enhanced by learning an appropriate distance metric from the assigned labels. Therefore, we adopt the triplet embedding loss as a second auxiliary loss function to regularize the latent space. We showcase the performance of GMVAE utilizing two PSD datasets with normalized pulses. All data are measured leveraging a recently developed deuterated trans-Stilbene organic scintillator. The total record length for each pulse is 592 nanoseconds. The data labeling for pulses deemed reliable has been performed using a standard method which consists of the total integral of each pulse and the integral of the tail of each pulse to compute the so-called tail to total ratio, TTR. The 2D representation using the total integral and TTR allowed the discrimination of neutrons and gamma rays using a quadratic boundary, and this method is referred to as the charge integration method. The first dataset under scrutiny is denoted by the three-class dataset, which encompassed three groups of pulses classified as alpha, neutron, and gamma ray pulses. This classification refers to the radiation interacting with the detector material. We train on 9,000 pulses from each class and test on 1,000 pulses from each class. The figure on the left shows one sample of each class of the training dataset, and the figure on the right presents the training dataset in 3D space projected by PCA. We evaluate the performance of GMVAE in terms of classification accuracy by training with different numbers of labeled data points, from 0 to 100% of the size of the training dataset. The accuracy of GMVAE is compared to a semi-supervised GMM implemented using the EM algorithm. The accuracy with labeled data is also compared to different classifiers for supervised learning. In contrast to GMVAE and GMM, which can be trained on both labeled and unlabeled data, the supervised classifiers are trained only on the subset of labeled data. The figure on the left displays the classification accuracy obtained by GMVAE, GMM, and the three best supervised classifiers. We can see that most supervised classifiers achieved high accuracy for all tests with labeled data above 5% of the size of the training dataset. Interestingly, GMVAE maintained the same high accuracy for all tests with labeled data just above 0.1% of the size of the training dataset. The figure on the right presents the 3D latent space of GMVAE with 1% labels projected by PCA. We can see the clear separation between the different classes for both the training and testing data points. The second dataset under scrutiny is denoted by the 4-class dataset and includes pulses belonging to 4 classes: alpha, deuterium, proton, and electron. This classification refers to the particle depositing energy inside the detector. We train on 9,000 pulses from each class and test on 1,000 pulses from each class. The figure on the left shows one sample of each class of the training dataset, and the figure on the right presents the training dataset in 3D space projected by PCA. We can clearly see that the pulses present similar shapes with subtle differences. The figure on the left showed the classification accuracy obtained by GMVAE, GMM, and the 3 best supervised classifiers for the 4-class dataset. This dataset represents a more challenging problem than the first dataset, where 2 of the classes, the deuteriums and protons, are very similar. The figure confirmed the superiority of GMVAE in comparison with GMM in learning meaningful features from both labeled and unlabeled data, suggesting that nonlinearities contribute to better classification results. Furthermore, supervised GMVAE reaches a peak of around 97% compared to around 92% for random forest that give the best results among all other supervised classifiers. The 3D latent space of GMVAE with 1% labels projected by PCA is shown in the figure on the right. The figure illustrates the high similarity between the pulses associated with deuteriums and protons. We also noted that the classification accuracy of GMVAE linearly increases by increasing the number of labeled data points. We presented a semi-supervised classification approach for solving the PSD problem. Our approach leveraged a GMVAE which can be trained in an unsupervised fashion. To increase the classification accuracy and take advantage of the usually available but scarce labeled data, we also introduced a semi-supervised GMVAE with auxiliary loss functions. We studied the performance of GMVAE utilizing two datasets with different numbers of classes. The results confirmed the superior performance of GMVAE compared to other classifiers such as GMM for unsupervised and semi-supervised learning and random forest for supervised learning. Our future work includes the use of GMVAE for the classification with piled up pulses or outliers. Finally, I would like to thank you for listening to this presentation.